from the same book, 1.44 hopefully. And then the name is very fancy for a simple one. It's called the can I switch? I did not. I hope I didn't switch them around. Bolzano. Because in the email, I kept going back and forth, right? Should I just double check since we're recording it? Sorry, let me double check. I don't want to mess this up. Bolzano. You gonna get some tea? Yeah. Is it really good?
Yeah.
Oh.
Oh, good.
Okay, so Bolzano, Weierstrass. 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 Is there a U? There is no U.
No.
Good. Good.
Never.
You never know, I know. Weierstrass. That's how you pronounce it. And it's called as usual, a theorem. And all right, so now we're all set. What I really like about this theorem is the one line statement of this thing. Every bounded infinite set, by the way, set of real numbers. So has an, so I need a third, so I'm going to do has an, and then accumulation or cluster point, has an accumulation point. So here's the deal here. So this set is not, it doesn't say closed, right? It does not say closed and bounded. It just says bounded. So therefore, it's kind of hard to, because if it is bounded, it can also be closed, it can also be open. So in my formalization, right, so maybe we'll have to do this. It might be closed, it might be open. A bounded infinite set of, let's say, A comma B. And bounded. So this is just closed and, closed, open, and then here we have the lower bound and the upper bound. So this whole part in red maybe is described like that. And maybe, you know, B is the least upper bound and A is the, right, depending on how it goes. And then over there, accumulation point, we already have seen, it is 0. And then S is the elements of the set S minus the accumulation point, which is X. So the distance of all the S's, all the S is the distance of all the x's from the cluster point x is epsilon, within epsilon. Yeah. So epsilon distance. Mm-hmm. A comma B is A comma B. So that's understood already. When you call something like this a set, you're talking about real numbers. When you talk about something like this, let's say Z, then you're not necessarily talking about real numbers. This could be a real number set, but when we're dealing with this, when you're dealing with things like this, those are definitely they're always real sets. Okay, so you don't have to state that by default, always. Otherwise, they don't make sense, and that's why the usage is so much. Okay, so that's a good question though. And then I'm just going to put here, just like in order to kind of give a visual, right, shorthand that I usually do, we're going to have this situation, and in this situation we're going to insert this reality. That's what's happening. So this is the world of a real number line with a set S, and it kind of looks like this. Here's a set S, and it has every bounded infinite. So it has a upper bound A and a B, upper bound B, and a lower. Do this, and then this is A. So it could either be closed, open on this side, closed, open, and it says bounded. And so, in other words, anything here too is also okay. So this is the world that this line gives us. This gives us this, which we translate into this. That is, we are opening up, elaborating, setting it all up. Once we have it all set up, we want to take this reality and stick it here. So I'm doing the meta here, right? And what is that reality? The reality is that there will be some x. All the yes, exactly. And this is the set S, and these are little s's, right? One S here, maybe another S here, and then this is x plus epsilon, and here they are going to cluster on both sides of the cluster point. So the definition allows us to set it up, and then we mess with it and impose this situation. As soon as this situation happens, we're done, and we do it twice. One for the left side of lambda, so LUB happens, because what does LUB guarantee you? LUB says to the left of it will be? Yes. And it depends on the set. So okay, so before we actually even look at the proof, what happens is this is what they do. You were going to ask me something, but what they do is, let's say this is the lambda, and we have the P is in a set. So this lowercase p is in an uppercase P set. And you can only be in this set if to the left of you, there are only finitely many. That's how you create. So what you do is you create a situation where there are only finitely many, and those are represented in today on the whiteboard here like this. These are finitely few. And so the set P, unlike in the other theorem, is a very simple one here. All it says is you can be a member of the set P if to the left of you there's only finitely many. If the LUB here is to the right of the rightmost element, then between this and this is going to be infinitely many. Then that won't happen. But anyways, so let's go back. So this is where we'll be heading, because we've done enough of wrangling here. Proof. Okay, I'm gonna write full lines. The proof is similar to the proof of Heine-Borel theorem. I'm gonna skip that. Let S be an infinite set that is bounded above by B and below by A. What are we doing? We are expanding the antecedent. We just have English, we're bringing in math. So we can actually work with this, right? So, so the picture we get here is, and this is where I want you guys, your input. It says infinite set that is bounded above by B and below by A. And the picture I drew, maybe it is wrong, but it seems to work. So the set S here, and this is A. So I'm going to write it in, oh, we're going to be using this picture for a little while. Okay, so what do I do? Do I do what I did here? Oh, I forgot about these things. What does it mean for set S to be bounded? That every element in set S is either less than or equal to. So the word bounded means above and below, right? We've done that before. So when they expand that, they bring in the letters A and B for that. So for instance, we could have set S is bounded by B here. Okay. And why I don't still understand this, I don't know. So that looks like, yeah, I mean, that's all we have from that sentence. Now it says define, now it gives us the, and again, this is a definition of a set P, a definition that comes into the theorem, just like inequality property. What was that? The inequality, absolute value inequality property thing that used to come in. The set P also comes in. It's not in the, at addressing Thomas's question from last time, in the statement of the theorem. Okay, and so they just define it, and so they go define. So define the set P So this is a tool that we need for us to prove the theorem. And this tool doesn't come out of here. It's an outside tool that comes in. Okay, so it's a set P that defines set P. Define set P as follows. And the book goes, a real number small p. I think I'm going to put this makes it a small p, right? A line underneath it. Small p in big P. I just remember seeing that somewhere. If and only if. So small, define set P as follows. A real number P is in P if and only if there are at most a finite number of elements of S less than small p. Whoa. That are so at most a finite number of elements of S that are less than small p, point p. Okay, so now I'm going to they just gave us a p and I'm going to put it in. So this is, use this color. Okay, and then big P will be always in blue. So we have P here, set P. And it's going to have small p, because when I put small p, let's say I put it, this is not big enough. So and we will have to adjust the A's and B's. Maybe not actually. Actually, we won't have to. And so here is small p. And P is in set P if to the left of P, there are at most a finite number of elements of set S. We discover there is, when we are looking at a infinite set S, we're going to find an element in S, and we're going to go, oh, after P, an element in S, like for instance, this guy here, P, after P, there are infinitely many. But before it, it seems to be a very few number of things. So just like we did in sequences and series. So this represents tragically few. So this is few. Finitely few is, let me do a better job than that. Because it's all about how beautiful it looks for the, here we go. So this indicates finitely few elements. And then many are going to be, and so here we have, and to the right will be infinite. And this, what we just changed the picture is because of this sentence I just wrote. So this is a definition of the set. So when we define the set, it turns out we also add a little p into the diagram and bring that into the proof. And the set p looks like this right now.
So what I'm wondering is, since S is technically an infinite set, there's no way a P could exist, but when we put a P in there, we determine chosen that there will be finite repeat elements.
What we're seeing is, it says here, every bounded infinite set of reals will have an accumulation point. And accumulation point means that before and after that accumulation point, the number of elements are going to be sparse. Most of the elements of the infinite set will be found clustered, bunched around this X, the cluster point. So every infinite set, this theorem says, Bolzano and Weierstrass found that every infinite real set has a cluster point. In other words, most of the numbers accumulate around one cluster point, one central point, and they're not evenly spread out. So in other words, it always looks like this. If they're saying it, because it's also a subset, right, of the real. So this will always be the case. This will be few, infinite. And right here will be our X, always.
One, still infinity, but with ones beyond that. Oh, and then you can just call that. Yeah. Yeah. Where bullet is one. Right. The way that it's trying to make it is like the X is the point that you're looking at. So if you're zooming into one specific point, that's going to be a cluster point.
This could be point number 10. Let's say it's like it starts at 1, 2, 3. Let's just call it 5 and 4. We did this in sequences. After 5, every point all the way to infinity is always going to just fall within the epsilon of our cluster point 5. It's going to be a Q, because if you have a P, a mathematician is going to like, where's my Q? So the Q comes in and he goes, observe, masters. Like in the British system, the young people call master. Master Thomas and Master Chris, observe that the font size has recovered. That if P belongs to the set P and Q is less than P, exactly, set P, then Q also belongs to set P. And their explanation is so weird because, so I'm going to write it in red because I don't like the way they expressed it. Because, or maybe you'll like it, because any element of S less than Q is less than P. And this is where I want to highlight this last bit here. This is the English sentence we're getting.
This is roundabout saying Q is less than P. Yeah, all this has been stated, but we didn't really need a Q. Q is just an example of the finite point.
Q is an example of another point in set P. And Q is in here, and it's to the left of P. because Q is smaller than P, so it's going to fall here. And guess what? Obviously, the definition of set P, it falls under that, because to the left of Q in set S. So in my notes, I wrote Q belongs to P because there are only finitely few elements to the left of Q from our picture. That's all.
So anything that belongs to
Hmm.
Q, then that's
Yeah.
fine.
It says, so because any element of S less than Q, so all the elements of S less than Q are less than P, and all elements that are less than P are finitely few. So set P is something this is an imposition. It's an imposition to create this situation, to get to this.
And could that last sentence just be what connects it to? Since before P could be anywhere, but now it has to have points in set or set F.
I think the reason why this happened, let's see if Q comes into the picture again. All they did is they told us that one part of the set, infinite set, has finitely few elements, and they gave us two examples. Q, P, so the difference, okay, I guess, I get it. The difference between Q and P is very huge. Q, to the right of Q, also it has finitely few. And to the left. P, finitely few on the left, on the right, it's infinitely many. Okay, I see what you're saying. What's happening is that these guys are always in S. And if these guys, any point in S that satisfies the definition of set P will then end up in the jail house. This is the jail house. Okay, let's move on. Here, few, many. Okay, I should have left it there. Okay, I'm gonna delete this. Antecedent, and this is consequent. And we're gonna leave our P there. And so this was all, what is it? Setting up the proof. Now step one happens. P has an upper bound. So this is the set P. Remember, upper bounds, least upper bounds, all of those things have to do with sets. That's why the sets come in. And also, but what it is that this kind of set it's not an imposition, it's more manageable. Manageable, if I can spell it right. It didn't mind. Manageable. Versus an infinite set is harder to manage and navigate. So that's why. Anyway, so I think what the book wanted to say was that you show this, and also it has maybe it wanted to say P has a LUB, lambda. And then I would say, this is what we need to show. But the book doesn't do that. So this is the book, and this is just me. So this is the first line of step one. And then second line adds another element to our set P. Let me create some space for it. So currently we have a P and a Q. And I purposely did that because I will have to go in and delete. So it says, notice that A belongs to set P because no element of S can be less than a lower limit. Is that what it really says? Lower bound of S. I'm like, where did that one? Lower bound of S. I don't buy any of this, but this says, notice that A already belongs to the set of P because no element of S, this whole thing, can be less than a lower limit, a lower bound of S. And
Isn't the greatest lower bound then?
or the bounds are in the set themselves. And yeah, because at this point, when the set ends, it is going to be infinitely many here in the blue area.
That's real number.
Yeah. So, but if we draw it right, I messed up here. See, this was the real picture, right? There are infinitely many right there before it hits A. Define P, set P as follows. A real number P is in set P if and only if there are at most a finite number of elements of S that are less than P. No, it doesn't have to be.
Yeah, because 0 is a final number.
Yeah, 0 is that's what I wrote in the notes. And it doesn't say that A has to be in S to be member of that. That's kind of messed up, but that's how they defined it. Okay. All right, so fine. And so 0, there are no elements. And no means 0, and 0 is a finite number. It is finite. Okay, next. So we have now 3 elements in set P. And thus, of course, because we're not looking for an upper bound, we already know it's B. What we're looking for is a LUB. So it says, and thus B, thus set P is not empty. And then the book goes on to say, further, P is bounded above by B. And the reasoning that they write in English is, since the infinite number of elements of S are all less than or equal to or equal to an upper bound of S, which is kind of weird. That's the hint LUB right down there. Okay, so we have the 2 conditions you need for the set P to have a LUB. P is not empty. It's got 3 stupid elements in it. And P is bounded. It has an upper bound, B. And then this, what is this doing here? I don't know. I still don't understand this bit.
I think that's just defining as an infinite set as since it's got infinite elements.
Mhm.
And so B has to be bounding the infinite set, so every element of that infinite.
Oh, it's the same routine we did in the other one. Okay. B bounds the infinite set, which means it's also bounding these guys. Oh, is that same weird less than the upper bound? Yeah, so A, Q, and P are also less than that same upper bound that the S has. So what they did is they said all elements of set S are less than B, and so are all the elements of set P, because all the elements of set P are in the infinite set, because this whole thing is infinite too. It's just, okay, that's just stupid. All right, let's move on. So, and then then they're gonna pull the axiom number 15. So I'm gonna write it here. We're running. And so the last step is, and that's why I was saying this is what they have to actually prove. But in fact, they have to prove both. It has an upper bound by just writing that sentence. And then now that we have shown it's not empty and it has an upper bound by axiom.
Point P has a bound, it's not empty, right?
Reason why this letter P, set P.
Does it have to be B because of the fact that it's bounding S?
Last time in the last proof we did yesterday, it said the reason why B is an upper bound for set P is that set P is a subset of set S. That was the reasoning they gave us last time. And this time they're saying is that these guys, it looks like that, but they haven't really, just like there was another line just like that, that these elements are smaller than the infinite part of set S. And if the infinite part of set S is less than B, so are these guys. Just saying that set P is subset of S would have worked too. And then everybody knows axiom 15 is our property or completeness property, which is the same thing. Okay, has, so by axiom 15, because of those two conditions, P has an upper bound lambda.
LUB or upper bound? Oh, no, it's upper bound.
It is LUB, least upper bound, sorry. Good catch. Has a least. And you know, LUB is everything, let's just say. LUB is your cousin, your mother, your father, your doggy.
LEB is just that one guy that they call like
The go-to guy, the go-to guy, right? Yeah, that's
do it all.
Yeah, do it all. It's the go-to guy. Lambda is an accumulation point for S.
Lambda of P or is this lambda of S?
This is the lambda of P. This is the lambda of set P, and because it's on this real number line, it is the second hand. As you were saying, does double duty here as an accumulation point for set S.
That means it's also part of set.
We will be adding it to P. If, one second, it can go into P if to the left of it they're finitely few, or it can sit right here, given. So remember, lambda is the LUB of set P, as well as the accumulation of cluster point for set S, two different things, kind of. And then he goes, given any epsilon, okay, I just want to know where they got this epsilon from. Oh, I know what's going on, you're right. We are now tackling this part. So we're done with the consequent. No, not consequent, antecedent. And now we're going to bring this in. So we are bringing this in one bit at a time into our assumptions. If our assumptions hold true, the way we have set our define our set P, if all of this works, when we bring this in, we'll get a true picture that there is a cluster point. And so this is coming straight from, so this is what I wanted to say. This underlined the I'll just box it. Boxed line comes from the consequent. We are now working directly with the consequent.
Okay, so step one tackled the antecedent. We did everything we could in the antecedent.
Yes.
And what we got from step one in tackling the antecedent was a cluster point, which is the lambda.
And lowest.
Yeah, we did get a cluster point from step one because no. All we got was an LUB for set P, and we don't know where it fits.
Okay, so step one, we took our antecedent,
Hmm.
we made our set, and then we imposed P upon it, and from P got a least up,
Mm.
or got a lambda as a point. That was least up down to P and lambda within.
And I'm going to go with both you, especially you were saying that. I'm going to go and put a lambda here, not in the picture yet, and a lambda outside. And I'm going to put question mark here and question mark here. So this thing is from step one. Step one tells us that there's a lambda LUB. Lambda is always LUB, so
It's greater than or equal
to. So here, all the elements of set P are less than or equal to lambda, and one of them P is equal to. Lambda is in the set. So,
yeah.
And then here it's outside, and both of those. Let's see which one the proof chooses. Or when one of them comes in and one doesn't.
Oh, because if lambda's outside the set, then you have, it has to be, lambda's outside of the set because it's an accumulation point. There's infinitely many on either side of lambda.
Because we're going to do left and right, exactly. When it is outside, you get all the cluster points left of the cluster point because lambda is the cluster point. When lambda is inside, everything to the left is finite, but everything to the right, yeah. Okay. So given any epsilon, and this is coming from box line comes from the consequent. There are two cases. I should have read. I should write it correctly. Two cases. And there are two cases to consider. And so in this, for our case, I think let's keep this in mind. Like when I resisted putting lambda on P, like we should wait for the proof to tell us, unless it's very evident where it is. And then we can always go back and stick it where it should have gone if things are not working. Okay, all right, so let's keep that as a strategy thing. Either, and the two cases are either lambda is in the set P, like this one here.
Wait, you broke the rule. That's not a part of the rule, you do not have to use the symbol.
No, this is no, this is fine. Symbols like that. Okay, symbols that come from logic. Yeah. So like for all symbols that come from logic are hated in mathematics. I don't know why. So you can do that in when you're taking notes in class, but when you're writing out the proof, you're going to say for all, for the upside down A. There exists. You can write that when you're taking notes, but when you're turning in your proof, you say there exists. These are rules that are actually you have to follow them, or they'll take points off on their homework assignments.
Yeah, 'cause it's informal, it's
Yeah.
Okay. That is within the.
And then this isn't. Actually, they are going to use both these cases actually. A P not as in the point P, but the set P. So if lambda equals, if lambda belongs to Bolzano, here we go. Let me just check. Yeah, they don't have the set anywhere. Cool. So I'm gonna say next is if, so this is our first case, right? So case 1, this is also not in the book. I'm just putting it there. Case 1, if lambda is in P, then lambda in set P, then lambda plus our epsilon that we just defined up here is not so our set is currently this one now. A Q P lambda. This is our set. Okay, and I could easily translate this into our picture. I'm going to put this here. I mean, epsilon.
Yeah, this isn't in the book, this is nothing formal.
No, this is just me. This is me. The pictures are me. The book.
Your symbol rules bother me, because you've used is not in the top part above the picture.
Wait a second. Whoa, wait, what? Okay. What?
No, I shouldn't really.
No. Tell me again. What?
This is compulsive, but so you've got lambda is not within P. And then you've got lambda plus epsilon is not in P.
Oh, that the book does that, not me.
Well, I think like this and like
So they keep switching, and I think there's a rule for that. Why this and then why this? I think if you read enough, you'll be also doing this. This is in the book. It's not me.
Okay.
No, that's a very good point. Like why, right? Why not do?
or why not have that
Yeah. Oh, sorry. This is if lambda is in the set, then lambda plus they could have done this whole thing long. Now let's write the second line, which is like the dumbest English sentence I've seen. I mean, it's one of those weird ones. This means, really?
I love that.
Really? This book is going to explain this? No, it's not. It doesn't explain. This is one of the hardest books I've read, especially since I have no math background. Yes. Actually, poetry helps just a little bit. Yeah, actually, my daughter helped. She wasn't. Yeah, that's her because of her pre-cal That's how I really got into it. I was doing math on my own, but then I had to do it seriously for a while. Even though I didn't really do a lot of problems, I would just do examples. This means that there are an infinite number, and I'm going to put this infinite number of elements, infinite elements, does it say? Number of elements of S. That are less than lambda plus epsilon. So what I, in my PowerPoint, I'm saying, this sentence allows us to place this guy. And all it's saying is, it says that this means that we still don't know where to place this guy, but we know where to put this. It says this means that there are an infinite number of elements of S, which is really just this section in our picture, that are less than, so lambda plus epsilon can't be this, because they're to the left of it, less than, left of it, right? That's another way. Less than is to the left of it, gloss. The definition, the point B? For B is the upper bound, and it's not sitting in the set P though.
But there,
Because to the left of it, the infinite.
Lambda plus epsilon isn't set P, right?
No. Look, this guy is not in the set, right? So so we have to place it where to the left of it, there have to be infinite numbers, infinitely many. And so we can place it anywhere here.
It's only to the left.
Ignore Chris.
What is that?
Why can't we just have a nice upper bound that just sits there?
The upper bound is positive.
Just sits there, like Pakistan's economy.
No.
Just sit in there. Well, actually, sliding down. Thanks to freedom and democracy, that was going to happen. Then, once we have placed that, we can place the lambda. And lambda, okay. No, we're gonna wait for the book to tell us where to put it. We're not doing any guessing, but only a finite number of these same, look how loquacious they're becoming, huh? Same elements are, but only a finite number of these same elements are less than or equal to B. Did I say B? No, that is wrong. To lambda. I want to do what Chris wants. Bring B into the picture. B is really annoying. I mean, what is it doing there if it's maybe it's the first lady. Since this is the key line, since lambda is in P. And how did lambda get into P? This is the only two possible positions because of step one. You were right that the LUB has to be right here. So, which means that lambda, yeah, where did I stick it in there?
I'd put it right on top of P. That way we don't have to change our graph, or we could change our graph.
I changed my graph. Yeah, because
So just
no, I think you might be right. Just stick it there. Actually,
unless they do something with P, but I don't
no. Oh, well, that's in step two where P and yeah. I think I'm gonna do what you're saying. So I'm gonna do this.
that's unprofessional opinion.
I've got an MFA in poetry. No, because you're right. If I stick it here, then I have to change the way it looks. So we're not messing with that. This is very good. So I'm gonna make P equals lambda. And we can make the change here too. We can do this. Because you're in the zone, I'm taking your advice. Yeah. And I need to fix this. Okay, we don't have time to fix that. All right, so that's good. Since lambda is in P, to the left of lambda can only be the finitely few, the brave, and okay. All right, I put that in there, and then the next sentence goes, so there must be at least, so there must be at least one element S of S, small s of one element of S between lambda and lambda plus epsilon. So when you have finitely few, there is no guarantee. So this is the density business that this is a theorem that we haven't done in the first chapter. When you have a density, you will always be able to find one. So we find it and it's right here. S. Look what we have now. We have S. We don't have X yet.
Well, isn't X or lambda? Or
Oh, sorry. Yeah. This is our lambda. Sorry, and S. So we got that.
Oh,
Yeah, we got a cluster point because the step two said right that lambda is the cluster point. And we have epsilon in there too. And so yeah. So now we just have to do what? Consequently, so I'm going to delete this. That's step two. That's the second part of this. And then you get because this time we're gonna get you were saying this is lambda. So the infinitely many are on the right side, and then we go to the left side. So consequently, yeah, consequently 0. Actually, let me put it up here. So we have, actually you can see it. If lambda is our cluster point, CP, and then it just clusters right and then stops clustering right in the set S. We're not talking about the whole real number line, right? Just in the set S.
Yep.
Okay, so consequently it says in the book, zero. Yeah, I can do the part for you guys. So lambda, you were saying, yes, you can see it because it's there. This is what we have. Yes. So now what we do is we add, we need to make it look like that. So we subtract lambda from all three parts here.
Because went to the very
Yeah.
Right.
Yeah. Okay, so I'm going to do blue here. So now, yeah. So this is and minus doesn't flip anything. So okay. So I'm subtracting minus from all three. Then what happens? These two guys cancel. We have a 0 here. This is fine as it is. And these two cancel and we have epsilon. Is it pretty close to that? Yes. Now, is S minus lambda positive? No, it has to be. Otherwise, we can't put the absolute. And very brilliant. It's greater than 0 and our figure. So I'm going to write this. So S is greater than 0 and look at pick. S is to the left of lambda. I mean to the right of lambda. S is a bigger number than lambda. Therefore, this is a positive number, which means we can put so you can put this on if this thing inside is positive. You can go from here to here. You can take it off if this is positive. Okay, so and therefore, and this is where the book starts. So this whole step is here. What we just did is this line. And then consequently, the book shows that lambda is an accumulation point of point S. All right, let's move on to step 2. Oh, no, I mean, sorry, case 2. Okay, so since now we assume the second case, so case 2, we assume now that lambda is not in P. So set P. Currently, we don't have anything in there, but the lambda is sitting outside. And actually, so I'm going to put in the other things here. So we had a Q, and we had a P, and then these were and then yeah. So this is few many infinite. Okay. I'm just getting confused. Okay, here's the thing. Lambda is not P for this picture. And then it wasn't, we would have had to modify the last one in order to put lambda here. We didn't, and I think it's fine. And so I'm going to put in the sets, the elements A, to write it here. Set P is A, comma Q, comma P, and then lambda is outside. And so between lambda and P are infinite many numbers. Okay, so this is good. So since now assume lambda is not in P, and this is our this line translates into that set over there and that figure. Since lambda is the least upper bound for P, for set P, there is some element there is some element P such that and again, sorry, such that if we have a new number like this, it will be less than or equal to P. Okay, finally. And P will be always less than the least upper bound. So this is least upper bound, LUB. Now, if I put lambda minus epsilon right here, what it does is then it ends up in set P, and that is the wrong way to go. So that's what the book says. So else, if we stick it here, it's going to end up here. And we don't want to change this, that we took forever to prove that this was. Okay, let me put it here, for instance. If we stick this here, then this thing is an upper bound for P.
Oh, yeah, now we've got another least upper.
Yeah, so we don't want that. And so, and that is the case that they dismiss. And so we don't put it there. And we put it to the left of P. And so we get this. This is what we want. So now P is between lambda minus epsilon and this. All right, and that is what we want. And therefore, for our set P, we have A, Q, P, and lambda will go in here. Lambda minus epsilon and P and the outside lambda. So this is the LUB. And this is one of the elements of the set. And why is it in set P? Because to the left of lambda minus epsilon are finitely few. Okay, next. Since man of chair, since P, this is just too low for me. That was a small set. Since P is in P, there are only a finite number of elements of S that are then small p. On the other hand, so since P is in set P, there are only finite number of elements of S that are less than P. On the other hand, On the other hand, we have this situation and it says that lambda is not in P. So since lambda is not in, okay, so this is what he's saying. We are not going to be able to find an S to the left of P, but we will be able to find an S left of lambda because lambda is not in the set P. And therefore, and we can see in our picture too. So P doesn't work out for us. We go to lambda and they go, and it says then, it says, so, yeah, can you read this on the,
Therefore,
therefore,
before the lambda, before the therefore, if you want to get technical, but lambda is greater than or equal to an infinite number of elements of that.
greater than or equal to infinite elements of S, which is true.
So
So,
must be at least one element of S, element lowercase s of set S
mhm.
between the point P.
So there must be an element at least so there must be at least one element S of big S set S between, does it say between?
Yep.
Between P and lambda, right? P and small p and the LUB lambda. And so this S goes right here. And so we have this situation. So I'm going to erase all this. So, okay, so P is greater than or equal to lambda minus epsilon. So it could have fallen on P.
Yeah.
When we did that. Okay, so, and then lambda. And this implies, huh? Oh, shoot. And this implies swag. This implies, and that's it. So this, which shows that lambda is an accumulation point lambda, okay, of the set S. I think that is good. All right, so now what we're going to do is we're going to take this guy and we want to make this look like that. So we have lambda minus epsilon okay, so if you look here, and then if we look at this and we look at what we want, it looks like P is not here. Lambda is, so this lambda and epsilon, both of these guys are here, and P is not. Since we have this equality here, we can get rid of the P, and so this becomes, next step, this whole thing is replaced by just this guy here. small s, and then lambda. So now we're almost, so we got all the things we need right here to, and what we need in the middle is minus lambda, right? So what I'm going to do is I'm going to subtract, we did this, I'm going to subtract lambda from all three places here. So we got lambda, so subtracting lambda. Now we have s minus lambda, just like the way we want. And then we have these two guys on the right and these two. So these two guys disappear. Cancel, cancel. And now we're left with minus lambda. Okay, now if we look at the picture, is this thing positive or negative? Mr. Jake, what do you think? The picture is up here.
Okay.
Is s minus lambda from the picture a negative number or a positive number?
It would be a negative number.
Negative number, okay. And we want absolute value. So what we need to do is multiply. So I'm going to multiply this thing. Let's see. I'm going to take it here. And I'm going to multiply this guy, the one I just put in the box. Multiply it through with minus 1. So I'm going to have a pause here. I'm going to cut all the rest.
Hey,
Yeah.
before we do that, I had a question. So a couple steps before, when we removed p from that initial equation,
Mhm.
why can we remove that?
Oh, because it's less than or equal to. So
Oh,
this is this says p is greater than or equal to this. So we can keep one of them because there's an equality.
okay, that makes sense.
So I chose this so that we get rid of the term p. That's a good question, actually. All right, so I'm going to multiply this expression with minus 1, and it's going to flip the less than symbol. So let's do this. So minus epsilon becomes plus, becomes positive epsilon. We bring in the minus here. And then we have minus 1 times 0 is still 0. And again, did not flip it. And as I multiply minus through, the less than sign will flip to that. You can see it was less than and now it's greater than. And now we can bring in our absolute value signs. Sorry, and there's a parentheses here. Minus applying to the middle thing, this guy. Now we can bring in the absolute value vertical bars, because this is a positive number. And here we go. And now we can take that minus 1 out. And now -1 becomes just 1, so we can ignore it. And we end up with this, which is the same as this guy. So this guy says S minus lambda is greater than 0. S minus lambda is greater than 0. And then this says, which is the definition of the cluster point, S minus lambda absolute value is less than epsilon, and that's what we have here. And we are done.